In the name of Allah, the compassionate and the merciful. Hello guys. My name is Salar Delavar Qashqai, and in this video we're going to talk about the structural rehabilitation and seismic retrofitting optimization with Demand Damage Index and then with Newton-raphson solution. So let's back to the last video which we used in here for our model. We modeled a square confined concrete section with the retrofitted plate and with 9 degrees of freedom, 2 sections and 1 element. And at the first we trying to find the plate thickness optimization and then plate length of this column separately with Newton-raphson method. In this video we're going to have an example about steel pipe optimization with 9 degrees of freedom, 2 section, 1 column element, and all the process is the same as a previous video, but our demand value is the damage index. You see, damage index is equals to demand curvature minus yield curvature divided to ultimate curvature minus yield curvature. So if we defined ductility damage index as for example 10% or 25%, so we can calculate the demand ductility, and based on this demand curvature trying to solve the nonlinear equations with Newton-raphson method. So in this process, for finding the yield curvature and ultimate curvature, we must first run the moment curvature analysis. So and then with Newton-raphson we can get the solutions with 1257 iterations. You see, it takes so much long time for running, and you can run it very well, but it must take much time, and most of the time you have converge problems. So let's back to the Python code. See guys, in here I wrote it in a Python code. You see, at the first we want to have a steel pipe thickness optimization, and I wrote many functions you see in here for finding the maximum absolute value from outputting of the openseespy data, and then trying to plot it, reading some data, finding the bilinear curve for our moment curvature analysis. You see that guys in here, dynamic analysis as a pipe section, so I defined it in here as a pipe section. 2 concrete plus 2 steel 0.2 define the different properties of the materials, and also definition of retrofitted section and also not retrofitted section for our 2 sections definition, and then trying to output our data you see in here, and trying to output the second element, first section, deformation as a rotation of this element, and trying to use it. And moment curvature analysis with the definition of axial load, dr as a number of increment, tr as a thickness of the this pipe, and ductility ratio as a dr, and other values for calculating the moment curvature analysis. And in here, if we run the moment curvature analysis, you see that it's going to be calculated and shown the blue as a rounded moment curvature analysis, and then bilinear curve fitted, you see in here. And based on this two linear as a bilinear curve fitted, you can find the elastic flexural rigidity or plastic flexural rigidity, and also ductility ratio and even overstrain factor. So in this analysis, you see in this process, we want to optimize the plate thickness with definition of the target damage index as a 25%. So if we back to this code, so we defined here as a 25%, and in each step we are going to calculate the ultimate curvature and ultimate yield, and based on this formula, the demand curvature is going to be calculated in each step. So our demand curvature is going to be calculated, and then it must be in here. Yes, in here, our curvature during the analysis must be less than or equal to the target curvature. So all the process is the same of previous video. I defined in here as a TR as a thickness of the pipe, in here pipe in our analysis for initial gas, and then run the analysis. So at the first moment curvature with the defined parameters going to be calculated, then I used this step for reading the outputted data, and then trying to read it, the outputted data, and then use it as a bilinear curve for calculating the bilinear curve. And you see, with this formula, we're going to calculate the target curvature, and trying to print it for each iterations, and then we do the nonlinear dynamic analysis, and then waiting for 10 seconds for reading the output data, and also F equals to curvature of the section during the analysis minus target curvature. I use this formula as a rotation divided to the LR for our calculation of the curvature, and then trying to plot the current maximum absolute curvature. And also all the process is the same for FA minimum and FA maximum. And you see, if we get the solution, so the result is going to be shown. If we run the analysis, you see that in each step target curvature is calculated, and current displacements are also at the first, and then for FA minimum, and f maximum, then residual. So this residual value is very sensitive in our analysis. So if you and most of the time you have a converge problem for running this kind of analysis. For example, you see that this residual value is the same as this, and you see we must work for better convergence with these values as epsilon for finite difference derivative, convergence, tolerance, and this value. If this value is going to very higher than, for example, 2 and 6, so you're going to solve the converge problem, but in some process you have a bad convergence, you know. So your analysis, your Newton-raphson analysis is very sensitive with these values for better convergence. And you see that with this process of the analysis, with the defined damage index, we can have a best fitted pipe thickness during the nonlinear dynamic analysis. So you see that, guys, in this video we do this analysis based on Newton-raphson method. This video is for educational purpose. Please have a comment and tell me know about this kind of modeling. Bye.